In this mini lecture, I'm going to talk about adding, subtracting, and multiplying radical expressions. So first of all, to talk about adding and subtracting radical expressions, I really need to talk a little bit about the idea of like radicals. So like radicals are radicals that have the same index and the same radicand. Now, it's sort of a hard word here, radicand. That just means the part inside the radical. So like radicals are very similar to what we had before with like terms, in that they can easily be added and subtracted by just combining their coefficients. So some examples of like radicals here, these first two both have just square root of 3. So square root, there's really little index of 2 in each of those cases, and their radicand, the 3's are the same. So those are like radicals. And here, negative 2x times the cube root of 4y and 10x times the cube root of 4y. Since they're both cube roots and the radicands are 4y, those are like radicals. However, 3 times the square root of 6 and 3 times the square root of 7 are not like radicals. They have the same index, 2, they're both square roots, but one has a radicand of 6 and the other has a radicand of 7. And this last example here, their radicands are the same. They're both 4's on the insides, but one's a 5th root and one's a 6th root. So those are not like radicals. The like radicals that I have above can be combined. So if I have 2 square root of 3 minus 4 square root of 3, I would just say, what's 2 minus 4? Well, 2 minus 4 is negative 2, so that would just be negative 2 times the square root of 3. Just like 2x minus 4x, right? If we had that problem, 2x minus 4x, that would just be negative 2x. So it acts exactly the same way as like terms. And so here, negative 2x times the cube root of 4y plus 10x times the cube root of 4y. The cube root of 4y just sort of goes along for the ride. Negative 2x plus 10x equals 8x. Most of the time, not even sometimes, most of the time we do not know we have like radicals until we simplify first. And that's going to happen in all these problems in example 1. So example 1, square root of 125 minus square root of 320. Obviously, we don't have like radicals here. The insides are not the same. But these can be simplified. Remember, the idea of a radical being simplified, I can't take out any perfect powers of the index. Now, there's no index written here. That means these are square roots. So I want to see, is there a perfect square that I can take out of the 125? And then I had what I called my leftovers. I'm not going to write this down every time, but just maybe this first one. So what goes into 125? Well, it seems obvious 25 does, and that's a perfect square. 25 times what is 125? If you need to, you can use a calculator. 125 divided by 25 would be 5. Now, in this next one, with the square root of 320, it's not so obvious what my biggest perfect square is. I could take out 4, I could even take out 16. There's sort of a clue in the first part of this problem. Are my leftovers going to be 5? If I'm going to end up with like radicals over here, I'm probably going to want a 5 there as well. So that would be my shortcut. But let's say we don't even think of that. What's something that goes into 320 that's a perfect square? Well, 4 certainly does. It also looks like, well, what else? Is there anything else that goes in there? 16 goes into 32, so I would think 16 would go into 320. So if I take 320 and divide by 16, I get 20. Okay? So I get 5 times the square root of 5 minus 4 times the square root of 20. Now, I've talked about this before, but remember, this square root symbol has one job: take the square root. Once it's done its job, it goes away. The square root of 16 is just 4. I don't take the square root of 4 again, right? The square root goes away, just like the square root of 25 is just 5. The square root symbol goes away. The problem with what I've got here is that 20 itself still has a perfect square as part of it. I could have taken out something more. So I can take and break square root of 20 into two square roots. 4 goes into 20, and I can take the square root of 4, and that leaves me a 5 here. So I would get 5 square root of 5 minus 4 times 2 times the square root of 5. So that's 5 square root of 5 minus 8 square root of 5. And then when I look at that, I just combine the coefficients. 5 minus 8 gives me negative 3 times the square root of 5. What made this problem a little bit long was the fact that 320 was a pretty big number. So if that number were smaller, I might have gotten the problem done a little more quickly. All right, so in part B here, same sort of thing applies. I don't have like radicals right now. They're all square roots, so I might be able to combine them together, but not as they sit right now. So the square root of 27 I have to divide into two square roots. Is there something that goes into 27 that I can take the square root of? Well, I think 9. Square root of 9 would be 3. Now 27 divided by 9 is also 3, so that's what I would get there. How about 18? Can I break 18 down into two square roots, one of which I can take the square root of? Well, you might say 3 times 6, but I don't know what the square root of 3 is or the square root of 6. So that doesn't work. But 9 times 2 works because I know what the square root of 9 is. And finally, the square root of 48. This is one where, 4 would work, 4 times 12, but 12 itself could be simplified as a square root. So there's probably something bigger. And if you look at that list of perfect squares that I had in the second mini lecture for 7.1 through 3, you can see that 16 is on that list, and 16 goes into 48. All right, so I take the square roots that I can, and the square root symbols then go away. So 5 times 3, square root of 3, minus 2 times 3, square root of 2, plus 4, square root of 3. So I get 15 times the square root of 3 minus 6 times the square root of 2 plus 4 times the square root of 3. So I have some like radicals here. The square root of 3's are like radicals, but that square root of 2 isn't. So I can put together the square root of 3 stuff. So the coefficients, I get 15 plus 4. So that would be 19 times the square root of 3, and I have to leave the 6 square root of 2 on its own. It can't be combined with the other term. Okay, I'm going to go to the next page here. All right, part C. This one actually is pretty simple. I've taken these off of your Math Excel assignment. Square root of 4 is just 2. Square root of 2, I can't really do anything with that. And so 6 minus 3 is 3. These are not like radicals, so that would be it. This next one, there is some work I can do. The numbers on the outside, they just go along for the ride. We've been seeing that. But now square root of 75, is there a perfect square that divides into 75 easily or evenly? Something I can take the square root of that divides into 75. I think it would be 25, because the square root of 25 is 5. And then what's left over, 25 times 3 is equal to 75. Remember, these numbers have to multiply together to equal what's inside the big square root. So my second term, the 5 just goes along, and now I'm going to try to get two square roots. They need to multiply to be 20, and I have to take the square root of one of them. Well, I think 4. I can take the square root of 4 and then 5. And then here, same thing with the 27. I think I can do 9 and 3. Okay, so I take the square roots I can. And all I've done here is I've said the square root of 25 is 5, the square root of 4 is 2, and the square root of 9 is 3. Those just came down. When I multiply on the outside now, 50 square root of 3 minus 10 square root of 5 minus 15 square root of 3. Again, I have some like terms, but not all like terms. I've got a square root of 3 here and a square root of 3 here, so those can be put together. 50 minus 15 gives me 35 times the square root of 3, and the minus 10 square root of 5 has to stay on its own. Okay, part E here. There's some variables involved. Don't let that distract you or intimidate you. I'm still going to try to break into separate square roots. Now, we talked about a variable is a perfect square if its exponent is a multiple of 2. Or if it were a cube root, I'd want to look for something I could divide by 3. If it were a fourth root, I'd want to divide by 4. Well, I can't divide, this is y to the first power right now, I can't divide that by 2. So y isn't a perfect square, and I can't find a perfect square less than it. 50 though, I know what goes into 50. 25 goes into 50, so that's a perfect square. What would be left over? 25 times 2, and that y is still left over. For my second term, the 3 sticks around. I break into 2 square roots. 18 is not a perfect square, but 9 is. It would be 9 times 2 to give me the 18. For the y cubed, well, I can't divide 3 by 2, so I look for the next number less than 3 that I can divide by 2, and that would be 2. So I could put 2 y's in that first square root, and I'm missing one that would be in the last square root. So now I take the square roots that I can. So square root of 25 is 5. Square root of 9 is 3. Square root of y squared is y. So I get 10y square root of 2y plus 9y square root of 2y. And these are like radicals. I can even include the y's as sort of part of that. 10y plus 9y gives me 19y times the square root of 2y. All right, let's go to the next page here. So page 3. All right, so we're talking about now the second part of this little mini lecture, multiplying radical expressions. I just use this product rule of radicals. The nth root of a times b is just the nth root of a times the nth root of b. We were using that in section 7.3 especially. But what we're going to be doing here usually is using this rule backwards. We're going to be going from right to left instead of from left to right. We use everything we've ever done with multiplying before. So like in this first problem, I've got a number outside the parentheses. I'm going to have to distribute. So it depends how good you are at this. At the beginning, you can just literally write out the distributing. So 2 square root of 2 times 3 minus 2 square root of 2 times 4 square root of 2. Okay, now in this first one, the 2 times 3 outside, that would just be 6 times the square root of 2. For this second part, when I have square root of 2 times square root of 2, that's my a and b here. My square root of 2 is like this nth root of a, square root of 2 here is like this nth root of b. Right, so that's sort of like my nth root of a, that's like my nth root of b. And so what I would get, if I did that, the outsides would get multiplied together. So 2 times 4 would be 8. The insides would also get multiplied together. 2 times 2 is 4. So the square root of 4 is just 2. And I get 6 square root of 2 minus 16 for my answer. Just a note here. This is something you sort of want to pay attention to, and it can save you some time down the road. Because of the definition of what the square root is, it's not a surprise that square root of 2 times square root of 2 is just 2. I really don't have to write this square root of 4 stuff down. That's sort of optional. I could have written 2 right away. If I have a square root times itself, the square root always goes away. I'm going to practice that in this next one. One thing I have to be careful of here, this is a quantity squared. There's no shortcut. I can't just square both parts and say I'm done. I have to write this out as the same set of parentheses twice. So square root of 5 minus square root of 2 times another square root of 5 minus square root of 2. And now I have to use FOIL. I have to multiply every part of the first parentheses by every part of the second. So I get square root of 5 times square root of 5. That's first, right? So I've multiplied first together. Now I do outer. So that's going to be a positive times a negative. So that'll be negative, and I get square root of 5 times square root of 2. When I do inner, I get something similar. I get negative times positive, so I get minus square root of 2 times square root of 5. And then when I do last, I get negative times negative, which is positive, and I get square root of 2 times square root of 2. You could have done some of this in your head. I could have just said square root of 5 times square root of 5 is 5 at the very beginning, right? I could have just looked at these two. Square root of 5 times square root of 5 is 5. And then square root of 5 times square root of 2 is going to be square root of 10. So I could have just went right to this line. Square root of 2 times square root of 2 is 2. Remember, there's really little ones in front of these square roots, so when I combine like terms, 5 plus 2 is 7, but then I get negative 1 square root of 10, negative 1 square root of 10, that gives me negative 2 square root of 10. Okay, I'm going to have to do FOIL on this next problem as well. I'm going to skip some of this square root stuff a little bit here. When I multiply the first two together, I get 2 square root of x times 7 square root of x. Well, 2 times 7 is 14. But then I take square root of x times square root of x. Well, that's just like square root of 5 times square root of 5 is 5. Or square root of 2 times square root of 2 is 2. Square root of x times square root of x is x. When I do outer, I get minus 1 times 2, so minus 2 square root of x, and inner, minus 9 times 7, negative 63 square root of x, and then last, negative 9 times negative 1 is positive 9. So I get my middle two terms here, those are like terms, so the 14x stays. Negative 2 minus 63 gives me negative 65 square root of x plus 9. All right, let's go to the last page here. So, two more examples. We're going to distribute here, and there's no FOIL involved. I don't have two sets of parentheses. Square root of 6 times square root of 6, I could say 6 times 6 is 36, but then square root of 36 is just 6. But again, that's that shortcut. A square root times itself, the square root always goes away. For this next one, the y on the outside is going to stay by itself, but I can multiply the insides together. 6 times 30 is 180. So now to simplify 180, that's in a square root. I'll do it a little bit longer. If you find the biggest square root that goes into 180, it's actually 36. It's 36 times 5. But let's say you don't see that. Maybe we look at that and say, well, I do know 9 goes into 180. It would be 9 times 20. But the problem is the square root of 20 can be broken down farther, because 4 goes into 20 and 4 is a perfect square. So I get 6, 2 times 3 is 6, the y sticks around, and so that would be my answer. All right, so just if you don't find the biggest square root right away, you're fine. If I would have seen that this was square root of 36 times square root of 5 right away, notice that would have come down here to my 6 and my square root of 5, and this y would have come down as well. So I could have skipped all that stuff in the middle. This last one's sort of a big FOIL problem, but again, keep track of if you have a square root times itself. Here I get 6 square root of 7 times square root of 7 when I do first. Square root of 7 times square root of 7 is just 7. So the 6 goes along for the ride. Square root of 7 times square root of 7 is 7. That was from first. Right? Now I do outer. These are not the same square root, so I'm going to have to multiply the insides together and the outsides. Positive 6 times positive 8 is positive 48. Square root of 7 times square root of 5 is square root of 35. I just multiply the insides together. Same sort of thing happens when I do inner. Okay, so I multiply negative 3 times 1. That's really what's in front of the square root of 7. I get negative 3. The 5 times 7 gives me 35. And when I go to do last, I can make use of this shortcut again. The outsides, negative 3 times positive 8 is negative 24, but then the insides, square root of 5 times square root of 5 is just 5. I don't have to do square root of 25, although you can if you want to. So 6 times 7 is 42. These terms are like terms and like radicals, so I can put them together. 48 minus 3 is positive 45. The square root of 35 just sort of goes along for the ride. 24 times 5 is 120, so I get negative 120. So 42 minus 120, I get negative 78. Plus 45 times the square root of 35. And that would be my result.